In this video, we're going to look into the forced and the damped vibration. Just a quick recap of what we have done before. We looked into natural vibration. Here's a quick recap. A natural vibration is also called a periodic vibration. In a free vibration, the time period is constant. And since time period is constant, the frequency is also a constant, because frequency is 1 by time period. The frequency of a periodic vibration is called the natural frequency, and free vibration have a constant amplitude. Now we also know that this is a ideal case because of friction. In real world scenario, the amplitude typically tends to die down. A damped vibration is a one in which the amplitude decreases over time due to the drain in energy to overcome frictional and other resistive forces. The time period or frequency of oscillation does not change here. So you can see the effect of dampening in terms of the curve, in terms of the sine curve. You can see that exponentially it goes down. Now it could go very steeply or it could go less steeply. Here, if this curve goes down like this, the curve falls down very steeply. So that means that there is more dampening. All oscillating bodies experience some kind of dampening in the real world. Now, dampening is not all that bad. It's sometimes desirable. Example, in shock absorbers and buildings, we want to make sure that we dampen any kind of vibration because we don't want vibration there. And in some cases, dampening is not ideal. Let's say, in your watch or maybe in your pendulum clock, you don't want the dampening to happen. So to avoid dampening, we introduce something called a forced vibration. Now, in a forced vibration, a good example of a forced vibration would be a swing. In a swing, you would recollect from your childhood days that to keep the string moving or keep this swing moving, you need to give it a push every once in a while, and you will find that the swing goes higher and higher. So this force you give every time the swing comes back, and basically you don't give the force here. Every time the swing comes back, sorry for my drawings, it's really bad. So every time the swing comes back, we give it a push, right? We keep giving it a push all the time. So this is an example of where we apply external force periodically. So this is called a forced vibration. Now, it's important to understand that we are not talking about not giving a force at all. Of course, if you want to get this pendulum into oscillation, initially you have to bring this pendulum to a position here at a higher height and leave it. So we are not talking about that initial force. We are talking about the external force that needs to be applied periodically to keep it moving or maybe to raise its height, right? So the first time force is not what we are talking about for starting your oscillation. So here's a definition of a forced vibration. It's a vibration of a body which takes place under the influence of an external periodic force. External periodic force is important. Acting on it are called forced vibration. The amplitude of the vibration depends upon the frequency of external periodic force. So if you push it at the right moment, then your amplitude will go higher and higher. And this is something you might have experienced with swing, motion of swing. But if you apply the force at the wrong time, your amplitude could go down, your swing could slow down. The frequency of that oscillation or vibration changes with the frequency of periodic force or external force. Another example of force vibration is speaker. Now, in a speaker, the external force is the current that goes into the coil, which is around the magnet, and because of that, the cone of the speaker, it moves continuously up and down. So the frequency is continuously changing over there based on the frequency or the signals that is coming into the speaker. Based on that, the frequency is continuously changing in that. So a frequency of vibration changes with the frequency of the external periodic force. So here are a few examples. So let's see one by one. Now, of course, we all know that when you set the pendulum to motion and leave it for some time, it would come back to its mean position. It would swing lesser and lesser, and later, it would, after some time, it would just come back to rest. So that's a dampening in pendulum, and here the external force is probably the air friction. To be precise, we can say it's a periodic external force. That means that the periodic external force, this external force of air friction, is always acting against the motion of pendulum here. Here is another example. We keep plucking the guitar string continuously. So continuous plucking of string is the external force. Here. And the object vibrating body is the string. Now, there are two force vibration here. So one is continuous plucking of string, causing the vibration of the string. Now, this vibration of the string causes vibration in sound box. So both these are example of forced vibration. So in the vibration in the sound box, which is this entity, is for this, the external force is actually the vibrating string, and for this, the vibrating body, vibration of string, let's say the vibration of string, the external force is equal to the pluck of the string, right? So there are two force vibration that's happening here. Another great example of force vibration are speakers. In a speaker, typically you have inside this is a cone, and over this cone there are coils, and this coil is connected to your 3.5 mm jack. This is 3.5 mm jack. This goes into your phone or iPod or whatever music system, and in the center is a magnet, and this magnet is placed here. So what happens is, as you send the signals of the music, the coil, it gets magnetized, and because of the interaction with the magnet below, this magnet, you will see that this coil moves up and down, and because of that up and down movement, you will see that the music is being played. So this is another example of force vibration. The external force is actually the electromagnetic interaction with magnet, and the vibrating object is equal to the cone of speaker. So these are few examples of force vibration. Now there is a very special kind of force vibration called resonance. So resonance is a type of forced vibration. Now, to understand resonance, you can imagine a very familiar case of a swing. In this motion of a swing, we apply the external force. If we apply the external force when the swing comes back at the final position, at this position, if we apply the force, let's say, it oscillates between here and here, the swing. If we apply the external force at this point, so external force at point, let us mark the points A, the swing position B, and C. So if we always apply the external force at the point A, then the oscillations of this swing will increase. So in other words, the frequency of external force, when that is equal to the frequency of swing, then or we can say the natural frequency of swing, then we can say that then resonance occurs. So resonance occurs when natural frequency of vibrating body is equal to the frequency of external force. Please pardon me, natural frequency of vibrating body is equal to frequency of external force and not external vibration. So that's when resonance occurs. So what are the consequences of resonance? See, the consequence of resonance is that the amplitude steadily increases. So in this case, the oscillation of the swing, if you map it into a graph, what you will see is, initially for first few rounds, the frequency remains the same because it's a function of your length, but after some time you will see that each time when you push at the right moment, the amplitude is steadily increasing. So in some ways you can say that it's opposite of dampening, because this curve is now going upward, and what you see is the time period between the oscillations are exactly the same. And let's say at this point, this could be the point A, when you're giving it a push, and it is going on the other end, which is C. So this is A, B, and C, and here it is coming back, and again you're giving a push at A, and again it goes into the B, it goes into the C, and comes back to B, and comes back to A, and again you're giving it a push. So if you give the push at the right point, then we have resonance. Consequence of resonance is increase of amplitude of oscillation. In the subsequent videos, we will see a lot of example of resonance. Please watch them, and let us do some checkpoint questions before we wind up. Here are the checkpoint questions. The last question, where you had to give a few examples of resonance, I urge you to watch the next video, in which you will see a lot of examples of resonance. See you until the next one. Ciao.